Okay, we're continuing with example problems from the limits of series section. So limits of series, another way of saying that is we're analyzing infinite series. We have a series and we want to think about what happens when the number of terms that are being summed goes to infinity. Does the series converge, diverge? If it converges, that means that the sum is equal to an actual number. What is that number? If it diverges, then there's no sum. The sum goes off to infinity or negative infinity, or just there's no sum, infinite sum. Okay, now one type of problem that falls under this infinite series category is repeating decimals, infinitely repeating decimals. And so what we learned back in high school or middle school, elementary school, is you can have decimals that, with a decimal like this, 0.8 with a bar over the top, that means that the 8 repeats forever. And similarly here, this means 0.46, where the 46 just repeats forever. 46, 46, 46, 46. Here the 516 repeats forever. Here you go 10.1, and then the 35, 35, 35, 35 repeats for infinity. But what we learned is that, so when you classify the different types of numbers, whole numbers, natural numbers, integers, etc., the category of a rational number was that it was a rational number is any number that can be expressed as a ratio of integers. And repeating decimals fell under that category. So any repeating decimal can be represented as a ratio of integers. Only non-repeating decimals like pi they have no pattern, you can't represent them as a fraction. All right, so what we're going to do is for each one of these, for each problem here, we're going to take the repeating decimal and represent it as a fraction. And we're going to do this using infinite sums, and specifically a geometric series sum, an infinite geometric series sum. That's what happens with these repeating decimals. You can represent all of them as a repeating infinite geometric series. And since we can find the sum of an infinite geometric series, and also infinite geometric series with the common ratio less than 1. And so since we can solve for that, the actual exact value of a infinite geometric series, then that's how we're going to write this as a ratio of integers. So what happens is, okay, here we've got, what is this 0.8 repeating? What you've got is, so there's nothing in front of there's just 0. There's no like number out here. Plus what? Plus, okay, 8/10 plus, and then 8/100 plus 8/1000 all the way to infinity, right? That's what this is. That's what 0.8 is, 0.8 repeating. Do you agree? 0.8 repeating is this right here. Assuming this goes to infinity, then that is 0.8 repeating, 100%. Assuming this goes to infinity, this pattern here. Okay, well, all right, if we ignore the 0 here, just focusing on this. What is this? This is, if we have it, we're multiplying each term by 1/10. And we're starting with a is equal to 8/10, right? 8/10, then we multiply 8/10 times 1/10. Then we multiply 8/100 by 1/10, etc., right? So what this is this is the sum from I is equal to 1 to n of, and we put the first term, the common ratio, and then I minus 1, but it's the limit as n goes to infinity of this. That's exactly what this is, exactly. Okay, but what is this? This is a mess, right? Well, this is a geometric series, an infinite geometric series. We actually know what this value is. Since the absolute value of 1/10 is less than 1, this is going to be a over 1 minus the common ratio. So 10/10 minus 1/10 is 9/10. And there you go. That's it. 8 over 9. 0.8 repeating is equal to 8 over 9. Okay, what about this? So 0.46 repeating. Now, since we've got, so we're going to, it's going to be 0 plus something. Since we've got a bar over 2 digits, then the common ratio is going to be 1 over 100, 1 over 10 squared. Because what do we have? We've got, this is equal to 46 over 100 plus, well, let's do it this way. 46 over 10 squared plus 46 over 10 to the fourth plus 46 over 10 to the sixth, and that goes all the way to infinity. All right, and so what is this? This is the sum from I is equal to 1, well, the limit as n approaches infinity, of the sum from I is equal to 1 to n of so okay, the common ratio you can see is 10 is 1 over 100, and then the a is 46 over 100, and we'll just leave it like that because it's going to end up simplifying here. So 46 over 100 there we go. And so again, if the whatever, however many digits the bar is over, that's going to be the common ratio. It's going to be 1 over 10 to the power of however many digits the bar is over. All right, so, but this is a geometric series with the absolute value of r is less than 1. So we've got a, the first term, over 1 minus r. 100 over 100 minus 1 over 100. So 46 over 100 times and that should be fully simplified. I don't think we can reduce this anymore. And that's it. Okay, so here it's just you do this. It's a little bit different because we have it's not 0 point something, but that's not a big deal because all you do is it's going to be 2 plus, and then here's the infinite sum. All right, and then the common ratio is going to be 1,000, 10 to the third. So 5/16 over 10 to the third plus 5/16 over 10 to the sixth, right? Because this right here, 0.516 is 5/16 over 1,000. 0.000516 is 5/16 over 10 to the sixth. You see, that's what we learned in elementary school about decimals like that. So, okay, 5/16 over 10 to the ninth, and it goes off to infinity. Okay, so what we've got is r is equal to 1 over 1,000, and a is equal to 5/16 over 1,000, and so this is equal to 2 plus the limit as n goes to infinity of the sum from I is equal to 1 to n of 5/16 over 1,000. But this, we know we can, is equal to 5/16 over 1,000 over 1 minus 1 over 1,000. 1,000 over 1,000 minus 1 over 1,000 is 999 over 1,000. Is equal to Okay, but that's not the answer because it's 2 plus. Okay, so 2 plus 838 over 333. Okay. Okay, here this is okay. So we 10.135 with the 3.5 repeating. So what is this? This is 10.1 plus and then the infinite sum. But then so it's the common ratio is still going to be 1 over. It will be will it be 1 over 100? It should be 1 over 100, yeah. So unless I'm mistaken. No, it'll be, so we start with 35 over, this is not going to be over 100, this is going to be over, this is the thousandths place. This is 35 over 1,000 is 0.035. Okay, now 35 over, and now we need 0.00035. So okay, let me 10 cubed. Now we need 0.00035. That's going to be 10 to the 5th. 0.00035. Yeah, so it's still, the common ratio is 1 over 100. It's just with these, it's confusing because what's confusing is what's the first term is a little more confusing here. Okay, so we've got the limit as n approaches infinity of the sum from I is equal to 1 to n. The first term is 35 over 1,000. The r is 1 over 100. Okay, but we know that this is infinite geometric series with the absolute value of r less than 1. So this is equal to 1 minus the common ratio, and then so 35. All right, so we've got, so what is 10.1? That's 10 plus 1 over 10 plus 35 divided by 5 is 7. 99 times 2 is 198. Okay. $5017 over $495. Okay, here, so the common ratio is going to be 1 over 1,000. And so we can put 1 plus okay, now here's the infinite sum. All right, we're starting with 567 over 10 to the 6th. Okay, and then 1/1000 is the common ratio. Okay, and so this infinite sum here, the first term is 10 to the 6th, so 1 minus the common ratio. Okay, so this is going to be 567 times, and then you'll have 1,000 over 1,000 minus 1 over 1,000, so 999 over 1,000, so we've got so 567 divided by okay, now that plus so 45,679 over 37,000. All right, so here we're just going to have 5 plus, and then the infinite sum is going to be 71358 over, so 1, 2, 3, 4, 5 over 10 to the 5th. And then so the common ratio is 1 over 10 to the 5th. So 71358 over 10 to the 10th. Okay, and so what we've got is, this is a geometric series with common ratio 1 over 10 to the 5th, and first term this. So we've got 71358 over, and then 1 minus. Okay, this is equal to 71358 over, and then times is going to be, and then this will be, okay, so 5 plus 190,451 divided by 33333. And there you go.